It's a false. 0 is 0, but the 0 is not 0. It's a false. False means you can out of the while loop. Okay, then enter critical section. Okay, right now time is 0. At this time, if process 1 would like to enter the critical section, so time is what? 0. Right? 0 is not 1. Is it true or false?
That's
True
true.
means it's an infinity loop. Right? You cannot proceed until when?
Doesn't it getting that first? Oh, and then it keeps returning into.
Time should be changing.
Yeah.
When will be changing? Right now, process 0 is holding the key. Right? Time. So after the process 0 complete this part, critical section. Then what is the exit section? Time is 1. So time right now is 1. Then this is a what? Keep checking. Time is equal to, it's not 1, it's not 1. Then finally, once this one is changed, this will be like this. Is it true or false?
That's false.
False. Then it can move into the critical section. Right? So at this time, there is another critical section in the process 0. Then we are going to run this same entry section. Then right now time is 1. 1 is not 0. Is it true or false?
That's true.
True. Which means can enter the critical section or not? Not. Because it's a while loop. While loop. While loop. Because right now the process 1 is using critical section shared data. Okay, then once this one is done, then time is exit section. Time is what? 0. And the time is changed to the 0. Right? Then 0 is not 0. Is it false or true? It's a false. So can enter the critical section. So this is how it works. Using what? One shared variable. This is actually the very simple problem. It's a key. Time is a key, kind of. Okay? Whose time is that? First 0, then 0 can enter. If when you are done in the bathroom, so you can give the key to so your turn. You can give the key. Then the other process can use the critical section, the toilet bowl. Then once this one is done, give the key back to the another one, like that. So we can use the shared variable to solve the basic condition. This is the average one using one shared variable. Let's take there are 3 requirements. So mutual exclusion, progress, and bounded weight. What about this one? Mutual exclusion is good or bad? How many processes can enter critical section in this algorithm?
1.
So 1. This is really good. So no problem. What about the progress? Can it be the deadlock or not? But
I don't think it can.
what if this is a shared data?
Yeah.
If this one is changed to the 2. So for example, after you use the bathroom, you gave the key. There's one person who is waiting for the bathroom, but you give the key to your friend who are in the library. Who is in the library? Then can the process 1 enter the critical section?
No.
No. Because it's a shared data, it may be possible. It's just not always a 0 or 1. It may be certain different value. Then nobody can enter the critical section. Okay? So because it's just the integer shared variable. So it may be possible, so nobody can enter critical section. So progress is not a good. The consequently bounded waiting, because it cannot get the key, it can be forever to wait for the key. So algorithm 1 looks like the simple, but it cannot address the progress requirement and the bounded waiting problem. So it's just a simple, the simplest way to using the key. Think about, if you lose the key, who can use the bathroom? Nobody can use that. That's the problem of the key, using lock. Okay, so this is an algorithm 1. Then, can we solve this problem? Can we address this? So problem is we have only one shadow, only one key. Key is the problem, right? So why not checking the status of each process? So this is the process 2, the 2 process case. So can we check the process 1, process 0? Is it using the critical section? True or false? And process 1, is it using the critical section? We can check the status of each process, right? Because the shared variable, the key, can be used by the another one who is not waiting. So if we can check so let's check whether the process 0 and the process 1 is using the critical section 1, Boolean. Using the Boolean variable, we can check the status. So algorithm 2. So algorithm 2, instead of a shared variable, we are going to use the Boolean variable. It's called here the flag. Okay? So true means, so when the process is entering the critical section, I'd like to use bathroom. So you can report to the operating system. I want to use the critical section. Then it's marked as a true. After you use, I'm not going to use this one. It's a false. So we are going to use the flag, the true or false for each process. Okay? So this is the entry section. And this is the exit section. So entry section, so if a process is the waiting for the critical section, flag true. Okay? So for example, the 2 process cases, the flag 0 will be true. Then we can check why another process. If another process is true, true means bathroom is being used, right? So can you enter the bathroom? If somebody uses, you should wait. This one is true. True means infinity loop. So it cannot proceed until when?
Until that one becomes false.
Another process. Let me write down another process. It's a J. It's a true and Y. The flag I. And this is a critical section. And X section is a flag. J is a false. So this is the process J, the 1. And this is the process I. It's a 0. Process 0 case. So the right now flag, this one is the entry, which means the flag J is a true, and flag I is a false. Okay, then this one, which means this one is enter the critical section. Then process 1 would like to enter the critical section, then this one will be changed the true. But when we check the another process, process J is a true, right? The process J is a true, so it's infinity loop, forever. Until when? Until the process J, the exit, the critical section, the flag, I'm done. So you can change the flag J as a force. So this is a force. The force means, so this one is a force, so you can exit the while loop and finally enter the critical section. Okay. Then this time, if the processor J would like to enter the critical section, then this one will be true. Then check the flag I. It's a true, so it's a forever. Until when? This one exit. So this one is a force. Once the processor, the I exits, the I is the force. And this one is a force, so you can enter the critical section and so on. Only one process can enter the critical section using flag. So we are not going to use the key.
Professor,
Yes.
the algorithms run at the same time?
Operating system always running. Then, in case the criticals enter the critical section and run this one. Mhm. Yes.
The OS regulator. So we have two processes, right? You have process 0 and 1. Only one of them can execute the entry section.
Yes, right.
So the question is process. So if process 1 executes its entry,
Oh, no. So entry and exit section will be run every time.
okay, but here I have a question.
Yes.
Assume that both process 0 and process 1 set their own flag to true.
Mhm.
They will both be waiting.
That's a good question. So we will check what happened in case both of them are true. So this is the second algorithm using software. Okay. Then we can check the mutual. So we didn't use the key this time. Instead, just checking who is entering the bathroom, who is using the bathroom. If somebody use the bathroom, I'm ready. If somebody not use it, then I can enter the bathroom like that without key. Okay? So using status. So check whether this is good in terms of the synchronization problem. So first, mutual exclusion. Second, the progress. And third, the bounded waiting. How many user can use the bathroom in this case? How many process can enter the critical section? Only one, right? So it's good in terms of the mutual exclusion. Then next, the progress. So as you ask, what if both of them are true? It may be possible both of them are true because it's a shared data. Somebody can set up the true and true. So if this one is true, yes, it's true, and this one is also true, and waiting each other. So flag J, true, and the wait. Y, flag I. So this one is to keep waiting, and this process is keep waiting. They are waiting because they believe, each process believe somebody used the bathroom. So there's no way to get out of this situation. So because of that, even the second algorithm using flag is not a good in terms of a progress. Consequently, the bounded waiting is not a good. Okay? So that is a really good question that we encounter such a problem. So what can be the solution? Key looks simple, but it causes the problem of this one and this one. Status, who is waiting, and also the same problem. What can be the solution? Very nice. So that is the Patterson's solution. Patterson's solution is the first synchronization solution, the synchronization problem solution. So let's see, what is the Patterson solution? So Patterson solution uses both key and the status. So turn and the flag. they can address the weakness of each other, the previous one. So let's see the example. So this is the critical section, and this is the remainder. So when a process enters the critical section, operating system run entry section. Let's take a look at the entry section. We have two variables. One is ton. You know the meaning of the ton, the key. So then flag is a flag I, flag J. So actually this is one variable and array with a boolean. So the meaning of flag is we'd like to know who is interested to use the bathroom. Who want use the bathroom? We don't want, because the problem of key is somebody may get the key, those who never use the bathroom, right? There's no way to enter without key. So we are going to check who is waiting for the bathroom. So if a process is entering the critical section, check, I'm interested, true. The flag will be true. Then key, turn is the other, because I'm going to use, so I'm done. If this one is open, okay, give the key to other, not the other. Only, not other person who are not interested. Only give the key to the other. Then check whether I'm able to enter. Currently nobody uses. So flag J is the false. This is the checking the another process. And turn is equal to J. So if neither of them, if this one is false or if this one is false, which means I can enter the critical section. Okay? If both of them are true, which means the other person has the key. And also currently using. So currently status is using, which means I cannot use it. Right? But one of them is a false, which means key, I have a key. Because somebody gave me the key. Or the flag. So they are not, another process not using the process, which means currently the bathroom is available. Critical section is available. So right now nobody used the critical section. So flag J is a false. The default value is a false. This is a false. Okay, turn is, though you gave the key to the J, but currently not using. So this is a false. So you can enter the critical section. At this time, if another process J, so process J enter the critical section, and the flag J is true. And then the turn is I. If I have a key, I can give the key to you. Then why? Checking flag J-I-N. And the turn is equal to I. Check. So right now turn is I. So because I gave the key. So I'm waiting, so if you have key, you can use it. So this is true. And this one flag I is currently true because it's being used. So it's true, waiting forever. Then, once the process I is done, X section flag I is a false. Because I'm done, I'm not interested. So this will be false. Once this one is a false, where is the false? Yes, this one is a false. So the while loop is a false, which means enter the critical section. At this time, if this one, process 1, again enter the critical section, then I'd like to use the critical section true. Okay? And also this one was true, process enter. Then the turn is J, then what is this one? It's a true. Turn is J, it's a true. So I process I cannot enter critical section. Waiting until when? When this one is done, process J, I'm done. Flag J is a false. So flag J is a false. Once this one is a false, this is a false, then the can enter the critical section. What if? So both of them are true, like the previous example. Even though this one is the both of them are true, but you give the key to others. So we can enter one of them, eventually enter the critical section. And also, even though I do not receive the key right now, it will be only one round waiting. Next, it will be my turn eventually. So in terms of the requirement, mutual exclusion, only one process is entering. Definitely yes. And the bounded waiting, progress. Even though both of them are true, you can use the toss the key. Okay? Then enter the critical section. Then the third one, bounded waiting, it will be only one round, which means one process cases. So this is actually called the Harrison, the solution. This is the first, really first, the synchronization problem solution used in the operating system. Problem. Any problem of this? You can prove this one by following. This is when you see the lecture note. So this is a timeline. Okay? And this is a process 0 or process I case. So this is a process 1, process J case. And this is the middle part is a shared variable by operating system. So you can, the first would like to enter critical section by the process 0. And this time the flag 0 is true and turn is 1. And so on. So you can use, you can understand this slide. And also you can prove whether it's satisfied with three requirements of the critical section, the synchronization problem solution, the mutual exclusion, and the progress, and the bounded waiting, and more details. That's the proof of that. Then, any problem of this Patterson solution?
It works great when you have two processes, but when you have multiple.
Yes, that's the problem. So we have only, in this case, two process cases. We can give the key to, we can extend easily the flag. Flag 1, flag 2, flag 3, flag 4, depending on the number of process. What about the turn key? Which one will get the key? In case of two process, it's another one. But what if we have the 100? Sometimes 100, sometimes 200, sometimes 2 process. Then you don't know which one will get the key. So Patterson solution is good, but it's only for the 2 process cases. Because of that, practically it was not used. However, most of the synchronization problem solution are based on this idea, the Patterson solution. Because of the Patterson solution still being discussed and studied at for the first solution. So there is the continue. Okay, so this is the Patterson solution. And then, however, in real life system is multiple processes. And also think about the architecture, computing architecture has been changing. Okay, so what if we have the multi-thread and the multi-core system? In this case, we are using the one shared data. But if we are using multi-threaded, which means the multi-core, each core has their own cache area. So it cannot be shared. Oops. It cannot be shared, so In case of modern architecture means multi-threaded or multi-core and multi-processor system. At that time, the problem is the shared data, because they have independent variable. So, for example, if we consider even two thread, okay, shared data, we cannot get thread 1, for example, would like to print X. Okay? Then that is the first set as X is 0, and the thread 1 is printing X, but the thread 2 is set 100, and our expectation is what? Print 100, right? But it may be 0. Why? Because this one is the instruction level. Okay? For instruction level, even flag true will be executed in advance before we change the variable, because it's may take the longer time. So because it's happened another thread, then the write down to the shared data, it may be displayed as the 0. So we cannot guarantee. Okay? So the slide showed such a limitation of Patterson solution. So it's not only problem of the two process cases. Nowadays, the multi-threaded, multi-core system and multi-processor cases is not the guaranteed. It's not issue. It's an issue. So how can we address such a problem? So we are going to use the name is this memory barrier. So memory barrier is if something changes on the shared data. So we are going to synchronize such a shared data along the number of thread, number of the core and processor. Okay, because we have the independent variable shared data for each the core. So in case the shared data is changed, but this one should be synchronized along the memory. So at that time you can use memory barrier. This is an instruction level, which means manufacturer CPU provide the instruction to synchronize the memory data. So this is called the memory barrier. So nowadays, so SMP machine, the symmetric massive processor. So if you are using the processor or the multi-core system, in your program, do you consider each core, each thread? No. SMP, the operating system, take care of that. At that time, such an instruction can be used to synchronize along the memory. So memory barrier. So for example, Linux, there the instruction name are varied depending on the processor type. So like sometimes the name is MB, the memory barrier. Okay, so SMP underscore MB. So or the similar name. Okay, there are two types of the memory model. One is a strongly ordered. The second is a weakly ordered. The strongly ordered is guaranteed. It's all stuff we need to synchronize. Then you can follow the order of the process. But this is too strong. The entire system will be hanged. It's a stop. So weakly order, we are going to try to make the order. Okay? But it applies, but we try our best. Like the real-time system. The real-time system, we try, the hard real-time system is guaranteed. But because of that, it's a lot overhead. System may be stop, hang, okay, stop. So similarly, if we are using when we are using memory barrier, because of this one, entire system may be stopped, okay, to synchronize. So instead of using the strongly order, most of operating system use a weakly order. So then the weak operating system try to synchronize and make the order it may be possible, okay? So it may be possible to use different order than unexpected data maybe happen.
Professor?
Yes.
So, since it's using like memory, doesn't that kind of like waste a huge chunk of memory since it's synchronizing every thread rather than using the...
Definitely it's additional space, the storage, but to guarantee, okay, the race condition problem, it's not huge, okay. The memory space is not huge, so operating system may use such a memory space.
So after like synchronizing, do they become independent, say one
Oh no,
process?
they keep because the synchronization will be happen forever while the operating system is running. So by the way, the operating system uses a lot of memory. So that is, and also important. That is the reason most of the operating system, the process and the data are reside on the lower memory for better performance. So memory is nothing but address. So it's a 0 to highest address. It may little bit take a time to find the higher address, the data. So most of the operating system reserve and use the lower the memory, the address, lower the address, the memory area. Okay, the very good question. So that is the memory barrier instruction. It really varies depending on your the processor. Okay. So this is just I never seen the memory underscore the barrier name is a pretend. So we can use such the memory barrier example. So Linux system use SMP underscore the MB, the instruction. This is a memory barrier used in the Linux or Unix system and so on. But each the operating system, each the manufacturer provide such a nowadays the memory barrier. Okay, so that. So far, the Patterson solution is the very well known, the software-based solution. So we learned about that there are 3 types of solution. One is hardware, another one is operating system, and then software. We have seen the software one. So first, the next one is a hardware-based solution. Hardware. What is a hardware?
Instruction.
Instruction. We are going to use instruction basically for law. So very basic idea is here. So it's in here. So we can disable the interrupt. Disable interrupt means what? Nobody can proceed the next because the interrupt, as we discussed the first our operating system nowadays is the interrupt-based system. It's a signal each other. So I'd like to use, especially to use the CPU, you need to interrupt and the dispatcher assign the process, and that process will be loaded into the CPU, and then until the next interrupt or next signal, it can be used. But what if you disable such an interrupt? Nobody can. So that is kind of system lock. Then enter the critical section. Then at the time enable the interrupt. For example, when you are managing the bathroom, so you can say the freeze for all students. Then pick up and wants to the one person to use that. Then you can unfreeze. Then they can do whatever they can fight for the next person, but for the next one, freeze. Then the select like that. So this is the hardware, the instruction. So there are several types of the instruction. So I'm going to introduce the 2 examples. One is the test and set the instruction. Another one is the swap. So old textbook use the swap the instruction. So but new addition of the operating system book, compare and swap. It's basically the same idea based on the swap. It's changing the value always. So first, this is the pseudocode of the test and set. The test and set, if you take a look at the pseudocode of this one, there's an input. Input is the value. Then always the target will be RB. This is a boolean, the true or false. And the return RB, which means input will be displayed. Okay? Input will be displayed. If input is true, and the output of the test and set will be true. If the input is false, and output is false. Okay? Then, what happens inside? Target is always true. So, which means, if the target, the input is true, output is true, and target is true. But in case of false, the output of test and set is false, then target is changed to what? True. Then how can we use this? So think about using bathroom. So nobody used. Okay, it's not being used. F. So if you enter the test and set, okay, you can return the F, but your value, target is changed to the true. It's being used. Like that. Okay, so one more important thing is that this is an instruction level. So one instruction, which means it cannot be divided, split. Once the instruction is not function in your program, function in your program has number of instruction inside. It may be possible interrupt in the middle. Okay? So depending on the application or your operating system, it can be debug, rollback. If this is the user program function. However, this is the instruction level, which means all or nothing. So we guarantee once we execute this instruction, it will be processed. Okay, then how can we use this one for the synchronization problem solution? So we are going to use the one shared variable is a log. So log is false, which means not being used. If log is true, it's being used. So if there is a process coming in, and the test and set the log. So right now, what's the value of a log? It's a false, initialized, nobody used. So this one is output is what? Always the same as input. So it's a false. Then inside, the input value will be changed to the true. So log is changed to what? True. Okay? In this, the test and set. One more time, the test and set, the return the same as input, but inside, value is changed always as a true. So right now it's a true. Then what is the output of test and set? It's a false. Because it was a false the first time, so output of the test and set is the same as input, false. But inside, log is changed as the true. So this is a false. You can get out of while loop, which means you can enter critical section. Then, what if there is another processor? Let me change it here. If another process is coming, so run the same entry section. So while test and set the log. So currently log is the true. So this one is a true. Return is a true. Right? True is forever. Forever, forever. Right? So then, when this current process is exit, the log is false. So this one is changed to the false. Once this one is changed to false, input is false, output is a false, then log is changed as a true again, then this process can enter critical section.
That's a question.
Yes,
But why the second process, why can't the second process run itself again and modify the log? Because the log is with a barrier.
log is a shared data, okay? So this, when the log is true, you can, log is false, you can enter critical section based on this one, right? But if somebody use, which means it's true, it's still true, so you cannot enter the critical section, you cannot get out of the while loop. Then, this is a multiple process solution. If you have another process run this one, same time, then the only one process can enter critical section. But problem is, progress and bounded waiting. It may be possible starvation, right? Because it's really long. Keep running. And also, there's one problem. If you have 100 process run the while loop. What happens when you are running the while loop forever?
You just keep going.
The CPU will be the 100% the utilization. Okay? So your system will be, it's the same as the infinity loop that you test in your the program. It's a happen. It's called the busy waiting. So busy waiting is kind of the everybody not under the toilet room. Okay? Bathroom now somebody there, then the entire bathroom will be crashed. So this is the solution, but you can get the idea how to use this one. Benefit, this one is not software. In case of software, it can be interrupt in the middle. That was also the one issues when you are using the software solution. But this is a hardware, so it cannot be interrupted in the middle, and also very fast because it's an instruction level. So it's very fast. There's no overhead bus there. It has a busy waiting problem, and also it doesn't solve the progress and the bounded waiting requirement. So before we solve such a bounded waiting and progress problem, there's another solution using the compare and swap. Its idea is very similar as the previous one, but the compare and swap is you are going to, there are input value and the expected value and the new value. Okay, the new value. Okay, then return is always the value, like the test and the set. Okay, this one will be return always. Then, if this value is the expected value, same as this one, and the new value will be assigned. Otherwise, if they are different, then they don't do anything, which means it's very similar as the test and set. However, test and set is true or false. True or false. But the compare and swap, it returns the input as it is, but as you can see, it's an integer value. You can set the what? So in case of test and set, it's only log, true or false. But using the compare and set, you can set any value, which means you can set up the next person using this one, like using the process ID. So I'm going to give my key after I complete using the toilet bowl to the next person always, +1. You can use the compare and swap. So compare and swap is the more flexible than the test and set. Okay, let's see the example of this one. So basically similar idea as the test and set. So this is the entry section. Okay, then there are three the parameter value. One is log. Log is 0 or 1 at this time. And then this is the expected value. This is the new value. So if nobody used the bathroom, nobody entered the critical section, and then log, the input is 0, output will be what? The 0. Raise return the same value as the first parameter, test like the test and set. Then compare whether this is the same as or not. They are the same. I expect the 0, which means it's free. So then I'm going to change the 1. So log is changed to 1. Okay? Then output of this one is the 0. So 0 is not 0, so you can enter the critical section. Then at this time the log is changed to the 1. Then if another process is coming in, then check the same thing. But the log is the 1, so cannot enter the critical section until the log is set as a 0. Two process case, but you can extend to the multiple process cases by assigning not just one. Log is the process ID number. You can set a +1 like that. Okay. So this is finally the solution using the compare and swap. Let me change it to this. 10 minutes. So let's see this part is a critical section. And this part is the remainder section, user code and the user code, which means this is the entry section. It's the operating system should provide this part. And this is the exit section. So this is the multiple process cases, general cases. Then see, waiting. So I'm waiting. It's a similar as what? The algorithm 2 that we have seen. The waiting. I'm waiting. Why? In the progress. Progress means we need to select the one process who are waiting the toilet bowl. Right? So we need to know who is waiting. If nobody waiting, just stop. There's such a synchronization problem. If many processes are waiting, how do we know? Check the waiting is true or not. So that is the reason it's true. Key is the log. Okay? Key is the log. Okay? Then while this part waiting, this is the similar as what? Patterson solution. The waiting of me. So this is and the logical operation, so which means in case of true and true, we cannot enter the critical section. In other words, if one of them is false, so key is 1, so definitely this one is true. Okay? Then if waiting is false. Hold on. This one is right now the waiting, and we have the key is 0. Okay, then enter the critical section. Then if so if both of them are true, then we are doing this one. Okay, I forgot the next the code. So compare and swap. So compare and swap means log is the return of this one is 1, right? So log is we have a log. Log is 0. Log is 0 and the return, the key is 0, right? The initial value of the log is 0. And this one is expected value is the same. Then we can just set up the log as 1. Then the key is changed to this one. A key is changed to the 0 because it's a return. Return of the compare and swap is the input of the log. So key is changing to the 0. Then go back to this logical operation, then this one is a 0. So it's a false. Then enter the critical section. Okay? However, if somebody used this one, log is 1. Okay, then the key is still 1. So this one is 1. Then is keep waiting until another processor who is in the critical section exit. Okay? One more time. So if nobody use the critical section, so this is a true, this is a 1, so this is a true. And we can use the compare and swap instruction. Then the log is 0, the default value. Then this one, the key is going to be 0. Then the log is changing to the new value, so log is going to 1. So the 0, this is a false, you can enter the critical section. If somebody use the critical section, which means log is already 1, okay? Then this log is 1, so key is 1, so it's still 1. Okay, new value is still 1. So waiting, then you can enter the critical section. Until another process changes. So if you admit, then waiting, because I got the key, so you don't have to wait. So you can set yourself as a false. Okay, so then this is the entry section. And when you are done, the exit section is the kind of what? It's a selection process. In case of two process, you can just give the key or leave the key. That's what we did, right? But this time, this is a multiple process case. So let's say there are processes 0, 1, 2, 3, 4. And this is the waiting. So waiting, all of them are false, for example, SRT4. And currently, process 0 is using the critical section. It's still false. Okay? Still false. But, for example, process 2 is waiting. And the process 3 is waiting. And process 4 is waiting. Then, check. Currently, the I is 0. I plus 1. 0 plus 1. So 1 is a j. So j equal 1. So j equal 1 is we are going to check this one. Is it true or false? False, we skip. Then going to the plus 1. And next. The j equal 2. J equal 2 is true. True means, so we can give the key to that. Okay? Then how waiting j is a false. Waiting j is a false means the j process, this one is a false. Then the j can enter the critical section. If this one is done, the process 2 is done, then next this one. And next this one, and next false, false. If this one is entered the true, this. So, mutual exclusion, very good. Only one process can enter. And progress. Progress, if you are waiting, you will get the chance to get the key. Right? Then, what is the worst case? One round of the process. One round of the process, eventually you will get the key. Okay? So this is the solution using the compare and swap. But still it needs what? While the busy waiting part is still because we are using instruction, so we can solve the problem without bounded waiting. Okay, yes.
You said the loop was the worst case?
Worst case means you need to wait. How long? Worst case is one round. Okay. So this is the exit section to select the next process. It's like that. I'm using the bathroom right now. So in this class, we have the 10 students. Not all 10 students are waiting for bathroom, right? So we have this is me. And this is not waiting. And number 2 is not waiting, but number 3 is waiting. So true. So I check. Are you waiting? No. Are you waiting? No. Then you are waiting, then you can get the key. That is the process like that. Okay, by changing the waiting as a force, and then where's that waiting is a force, so that process can enter the critical section. So this is the solution with compare and swap, and also bounded waiting. So in terms of the 3 requirements, this is the perfect. And so I already explained about the test and set. And this is the old version. I put the older version also, but it's just basically same idea. And we can enter critical section. Then this is the exit, and this is the entry. Okay. We have only 3 minutes, so I'm going to stop here today's lecture, but I think that I covered the most important part of synchronization, the problem. So we are going to a little bit speed up, and then the next week, we will see the real example. So this process synchronization problem is not only for the operating system. Nowadays, even application program, whether or not you realize that sometimes your program language provide such a synchronization solution, like when you create a multi-thread, then how can you guarantee the shared data? Then the programming level, they are using this. Also, explicitly, you can use the synchronization, you can provide the synchronization solution in your program. At that time, we are going to use a semaphore. So it's kind of a law, okay? As you can see, most of the such a solution, we can understand as a law. But problem is whether it can guarantee the bounded waiting and the progress. So next class, we will see the using semaphore and the monitor. And then we will see the example of the synchronization problem. Okay, so any questions? Please keep working for your project as well as the homework and the exercise a lot. Okay, so thanks so much.
I have a question.